Hello, welcome to the SkyFire DIY laser cutting machine contest. I'm Craig, and I'm going to outline what we ended up doing with our SkyFire laser. And first of all, I'd like to thank SkyFire for having this competition. Rob and I both run this shop here in Western Colorado, and I'm an electrical design engineer, but with about 40 years of experience. And Rob is a mechanical engineer with probably 20 plus years of machining experience. And we do some lightweight fabrication over here. We don't do anything structural. Our goal in the shop really is to do more ornamental as well as maybe sculptural type work. And I can give you an example of that. So this is a project that we made with our plasma table. This is a lampshade that my sister made when she came to visit, and we made this with a plasma torch. And this was a design. I'll show you some. I'll show you some more detail of this design. Okay, so here's what this looks like. So she brought a design up. We put it in our tool. We cut it with a plasma torch, and she bent it on a box and pan brake, and then she powder coated it this forest green. This is more in line with our goals for this shop, is to do things at this level. We can, comfortably work up to 1/4 inch. We can go a little further if we wanted to, but we're not really geared for that type of work. And so uh, uh, all of us have watched probably hundreds of laser welding, laser cutting, and laser cleaning videos, either on TikTok, Instagram, or YouTube. And they're just, it's great. We just decided we had the funding to go ahead and buy it. And what we ended up buying back here was a SkyFire Blazer with a 2,000 watt max fiber source. And over here, that we had that outfitted with a, what's it called? It's called a super laser cut SUP 23T laser head, which is a multifunction head. It allows us to weld, it allows us to cut and clean. And we took delivery of this about 9 months ago, and we love it. We love the whole thing. This thing works great. Turn it on, it works every time. We haven't had any problems with it at all. And in fact, if we did have problems with it, there's been a couple of occasions where we asked SkyFire for some technical support, and we got immediate answers back. And from our perspective, SkyFire is a great company to work with. All right, let's do another one just for fun. Okay, so let's talk about the laser swap itself. So what we have back behind me is a Langmuir Systems Crossfire Pro. It is a plasma table, CNC plasma table, and we have the torch height control for it. And this has a work area of 48 by about 32, 33 inches. And I've had this for about 5 years, and it's a very reliable machine. We've cut hundreds of projects on this, and I would love this as a machine as well. Um, Originally, it was out. It came with a Cut 45 plasma torch, handheld plasma torch, and I ended up buying this machine torch for it. And this was mounted on the XY platform, and since it had torch height, it also moved up and down with Z. And with that, like I said, we cut a lot of projects with that. There's some drawbacks with using a plasma torch. The first one is the kerf width on a plasma torch for us was about 60,000th of an inch. And when it's cutting a little bit slow. So what's happening is, because it's slow, it heats up the metal a lot, which ends up having a little bit of metal distortion as it's cutting. So we opted to get the torch height control to overcome any kind of warping that goes on while we're cutting. And also, that kerf width is blown out. We're using 125 psi air, compressed air, and we blow out the liquefied metal into a water table. And that water table is right below the cutting surface. And as that um, uh, uh, as that liquefied metal hits the water, and because it's, it gets blown out a lot, there's a lot of water coming out. And so what would end up happening in a shop, if we use the plasma table a lot, would get dirty. It's a really dirty process. A lot of powderized metal around here on the floor, and it just is kind of a mess. And we would end up using this. We'd drain the water table every time we used it and cleaned out the water table. And by doing that, we ended up having a lot of accumulation of this powderized metal in the water. And it took us, when you wanted to cut something, you'd have to come in and turn it on and fill up the water tank, the water table, and that would take about 15 minutes with our pumping solution. And so we have those things there, and then at some point we got to change the water out. So that water is going to go somewhere. We're not going to pour it down in the municipal sewer, because it's got a bunch of metal particles in it. So we have to dispose of the water that has been used for plasma torch. Okay, so those are the drawbacks of using this machine. So I'm going to move on to our solution for the laser swap. Okay, now the beauty of this approach is that when I do a pierce time, when I pierce the top level, it actually goes up it comes out of the bottom. But because I'm in the middle of my slot, when I flip this part over upside down, when I cut the second side, the piercing on the second side will go through the slot of the first side. So it should be good. So let's go ahead and try this. So I'm running compressed air at 125 psi. I'm 1500 watts. My feed rate's 120 inches per minute. And we're going to go here. So we're going to turn off dry run, and ready to go. Okay, it looked pretty good. So raise up here a little bit. Get out of the way. Here's our slot right there. So what I'm going to do again is I'm just going to take my piece, turn it upside down, run it again. All right. Change my speed up here a little bit. Okay, let's take a look at this tube. So we got squared ends. They look pretty good from the top. No blemishes, nothing. All right. Well, I call that a success. Okay, here's what we end up doing for our project. We ended up taking the machine torch off of this table, and we needed to mount the laser head, the multifunction laser head, on the table. So we first mounted it using the machine torch mount, but we really couldn't get it really didn't fit the laser head very well. So we ended up designing a 3D printed part that fits into the mounting screws on the back of the Z-axis on this machine. and we'll go ahead and show you that here. We have a model of that, and we just 3D printed it, and it holds the head securely in. And then when the fiber bundle has to go up and have a lot of flexibility in the fiber bundle. So it ends up, it dangles while it's up there. And then the original machine had this bar on here holding the cabling and the plasma torch. So it was just a bar that ended up with a bar. So you don't want to really kink the fiber bundle. So we ended up fabricating a 3D printed fixture that mounts to the top of the bar, and it allows the fiber bundle to have a very gradual bend at the top of the arm. And then to come down the arm, we ended up fabricating some brackets to hold the fiber bundle in. Now, we use this also as a laser welder. And so we need to be able to take this off to laser weld and put it back on quickly to do laser cutting. And so we have just thumb wheel here. We can loosen this up and pull this out. And then and this is loose. So then we take this and gently pull this whole fiber bundle off, and then we can use this as a laser welder. When we end up switching the head part here, the nozzle. All right. And then if we want wire feed, we add the wire feeder back on it. So we have 9-gauge 3mm stainless steel here and a 1500-watt SkyFire laser attached to our Crossfire Pro, and we're going to cut out a little sample out of this. So go ahead. So go ahead and pick this up. And if we look at the back side, there's a little bit of dross there, but not much at all. So let's talk about the laser, the way that this laser ends up working. So there's two circuits that need to be activated in order to enable the high power laser. The first one is the safety system. Now, when these come shipped from the factory, they come with the alligator clip, which I've seemed to have lost. Here it is. Okay, so this is just like a traditional welding ground clamp. And so when you're welding, in order for the welding to be safe, this has to be touching this. Actually, what ends up happening is the tip of this has to be contacting ground. And what that does is make an electrical circuit inside the controller in the main machine here. So that's the safety system. So if you pull this head off of your stock when you're welding, it disables the high power laser. So you have to have this touching all the time. Okay, so most people, if they're using it, they could potentially circumvent the laser safety system by doing this. The other thing that has to happen is you have to pull the trigger. Okay, so you engage the trigger, and that is another circuit that needs to be closed in order for the high power laser to be turned on. So both the tip of this has to touch ground and this switch has to be closed. Now it turns out coming out of this head are three wires for the control of the fiber laser itself, in addition to the fiber and the control circuit to run the servo in here and that kind of thing. But there's three wires that come out. One of them is the ground wire that is not the body of the thing. It's the ground wire comes up to the switch. So you have one ground wire coming up, and then the other side of the switch goes back to the controller down in here. And we'll show you that and where it's connected up over here in a little bit. And then there's another wire from the tip here that goes back down to the controller. And by pulling the switch, you make that connection on that circuit, and it touching this to the ground, you make that circuit. Okay, that being said, when we're using it as a plasma cutter, we need to circumvent both of these circuits. We need to connect the safety system signal to ground, and we need to connect the trigger circuit to ground. Okay, both of those have to be the case in order to turn on the laser. And so what we ended up doing for this is when the original Crossfire Pro came with a control system to control the plasma torch, it has a relay output that goes to the plasma torch to turn the torch on. And so that's the two contacts on a normally open relay. When the control system wants to turn the torch on, it closes that relay contact, and you get both sides of that contact. So for us, we wired these two signals in to act like the trigger on the gun here, the laser head, and then the other circuit we needed to do was the ground circuit. So what we ended up doing for that was we wired in this foot switch, okay? And in order to use this as a plasma cutter, a laser cutter, you go use the control system just like you would. Nothing changes at all on that. And in order to use it, you have to put your foot on this and close this circuit. And then the control system in here closes the other circuit, the trigger circuit, to turn the laser on. So when we're using it, you have to put your foot on here and watch the whole thing. And if there's a problem at all, take your foot off and it turns the laser off. So we do have a safety system still in place. We're still using it, and we're serious about safety here. So this is the way that we ended up wiring up. And I'll show you the points inside of here that need to be connected together, where they go into the controller. So basically on the back side of the top, we ended up drilling a hole, and we put a 3-wire connector on the back of this control box. And then we ran wires down through the enclosure, and we ended up going to this location on the control system. And I found what these pins mean by looking through the manual that came with the Blazer system. And so there's 3 wires there. There's the ground coming up from the gun, the head. That's the ground going up to the head, and then there's the trigger signal, and then the safety system signal. And you can exercise all 3 of these circuits by looking at the diagnostic screen on the Blazer system itself. Will tell you when those switches are engaged and when they're not engaged, so you know that you'll have it wired up correctly. All right, so here's our safety switch wired in, and over here you can see that there's the which one goes here? The secure lock signal. It turns green when this is closed. Okay. And likewise, if we were to do a dry fire if we control the plasma torch from the SkyFire control system, if it's wired correctly, you should also see this signal going here. You should see this one going. Okay. So when you're wired correctly, that's what you should end up seeing. Let's talk a little bit about some of the 3D printed parts we created for for our laser swap. So the first one was the laser head mount, which we talked about back here. Okay, we have this. We have the the fixture that goes up on top that keeps the laser bundle from becoming kinked at the very top of this arm. We have the brackets going down to hold the laser bundle onto the arm. And those are just basically slots that it rests in. That way you can take it off easily and not have to fix it. You know, you don't have to put any zip ties or anything on it. You just fit in that slot. Um, uh, we printed this screen cover here. We 3D printed this to keep from accidentally banging something on the touchscreen. So this is just printed with PLA on a Bamboo Lab X1 carbon. And up here above, on top of our wire feeder, we have 5 holders for our safety glasses. Okay, so these are also 3D printed, and they have embedded magnets in the bottom. So and then they come in this case. So we have 5 of them. These 4 are for people without glasses, and then this one's for people with glasses, which is me. We have a gray one over here, which is where we keep all of our extra consumables. And it too has magnets on the bottom. And then we have our consumables all come in this little aluminum box or steel box. And then our 3D printed some magnets in a frame. So this frame fits inside of this steel box on the bottom. And then over here, there's enough surface area on the other side of the handle to affix it right to the top. So these don't fall off. They're actually in there being really secure. And we know where all the safety glasses are. So that's very convenient for us to have. And one last thing is, when we're using this as a laser cutter, we want to take off the wire feed. So we have a way to coil up the wire feed shroud cable here. We can cable it back up again, and we can hook the little head that goes onto the laser head. We can hook that onto a 3D printed hook, and it keeps everything in place. It's very neat and we don't have any trip hazards in our shop, and it keeps everything very secure. So one thing we did do was we put push to connect fittings on everything, so we can easily switch from between compressed air and argon down here, and then over here nitrogen. So all we got to do is pull off our tube. This is a 10 millimeter OD tube, and we got 10 millimeter to quarter 20 MPT thread parts for these flow meters, and it's just a matter of putting it on there like that, and that's how we can switch between shielding gas and back over to compressed air. Okay, over there we got the stainless steel water table taken out of our Crossfire Pro. And here's our plan, is that instead, we were going to move the frame back. We decided not to do that. Instead, we just are going to protect the frame from the laser beam. This is actually the part of the shipping angle iron that came with our Titan 25T. I mean, our Langmuir Systems 25T. And then down here, instead of blasting onto the floor, I have the original table had a water system down here on a piece of MDF. I just covered this with a piece of like 14 gauge sheet steel. And the thing we're looking at now is the laser head here is it's probably about almost 3 feet down. And you can see the alignment dot down here is about the size of an inch in diameter. And so what we're going to do is we're firing at 1500 watts. We want to see what the actual intensity is of the laser beam itself. So go ahead and fire that for about probably about a second. And we'll check on what that's doing. And then move it out of the way. Okay. So this is what the intensity is. Down here, that little dot is probably about 7 or 8 millimeters in diameter. So I think this is going to work fine. And the original slats that I had, of course, this turns on. The original slats that I had are going to fit across the width of the thing here with the original angle iron for the slats. So we're a shop here that uses Autodesk Fusion, and all of us have a copy of that. And our workflow is to do our CAD design in Fusion. And we have two options to output machine files. One of them is you can use the post that comes from Langmuir Systems in Fusion to create the job file, the CNC command file, NC or whatever file. And you can use that and just import it right into the control system that Crossfire, the control system is called Fire Control. You can import that directly. But that doesn't give us a lot of control over various things that we want to control. And one of them is the heat distortion, and as well as some other parameters. And we end up using SheetCam for that to take a DXF or an SVG file that comes from either Fusion or Inkscape or whatever. And that will take that vector file and convert that into machine file, and we use SheetCam for that. And then we use, like I said, the fire control that came with the Langmuir Systems, unaltered. You don't change anything on the plasma table side at all. All you do is really disconnect the two wires that come from the control system for the plasma torch to turn on, and you wire that into here, like I've already outlined. So the first thing we wanted to try was there's a setting in anything having to do with generating this in the CAM section where you generate this machine file for the whatever you're going to run, is what do you set the kerf width to? Like I said, we use 60 thousandths for plasma torch, but what do we use for this? I mean, we know the cut is very narrow, but what actually is it? So we measured it. We think it's about 6 thousandths, so that's a tenth of the width. But But so when we put it into the fire control system, we put it into sheet cam, we did a bunch of calibration cuts. And I'll show you what one of our calibration cuts looks like here. You know, so we ended up doing something like this, where we had a 1x1 square with a 1/4 inch hole in it, and we ended up dialing in the kerf width setting into sheet cam to get this to be able to have really accurate cuts. And it turns out, for some reason, I think we set it to 0, and that enables us to get everything really accurate. We just worked our way down from like 10 to 5, and we just kept going, and eventually we got down to making it 0. And this is you know, little sample pieces like this show us how accurate it is. So Rob is over here. Why don't you come over and measure this thing from your perspective? Okay, so this is a 1x1 square, so we're off by 2,000 on that dimension, and over here we're off by 2 again, so we're really quite square. And then go ahead and measure the hole. So this is a 1/4 inch hole, so we're off by 1/1000 on this hole. It kind of depends, it's not quite round. Yeah. We were really quite surprised at how accurate we could get this thing to you know, for precise cuts. The other thing is, like I said, on the plasma torch, these edges are they're perpendicular. That cut edge is straight up and down, and that's inherent in the way that the plasma cutter works. I mean, the laser cutter works. We're going to talk a little bit about the Dross that's on the back side. Now, in our shop, we have 125 PSI compressed air, and it's fairly dry. And during the cutting operation, the laser liquefies the metal, and the compressed air comes through the head and blows that liquefied metal out. And what ends up happening is, because our compressed air is so low in terms of PSI, it actually cools the liquefied metal as it's coming out of the slot, and it reattaches itself to the backside of the stock you're using. So for us, I went over to our local fab shop over here that has like a 12,000 watt fiber laser, and asked them what they're using, and they're using 300 PSI compressed air, and they're not using nitrogen or anything, just that high of a PSI, and they're able to blow that liquefied metal out at such a velocity that it comes out of the slot a lot faster, and it doesn't reattach itself to the backside. So we tried that here. We can't increase the pressure of our compressed air, but we can with nitrogen. So we bought a nitrogen tank, and we got it retrofitted up, and we kept increasing the pressure on the regulator up, and we got up to about 220 or 230 PSI. And that, when we got to that point, the control system couldn't open the valve inside here to let the shielding gas get through the system. And that's because there's a rating on this valve inside of here. They can't handle those high pressures. And for us, we had the same amount of Dross on the backside with 125 PSI as we did with 220 PSI nitrogen. And so we just used compressed air, and it's fine. You know, it doesn't cost us anything. So I'm going to show you some examples of this Dross on some of the parts here. So just to show you, this is I think this is about 12 gauge here. And this is the compressed air part. And so you can kind of see what this Dross looks like over here. Okay. And sometimes your cut part doesn't come through because the Dross comes out, and the Dross itself reattaches to both sides of the slot on the backside. So sometimes your part doesn't come out, but this is loose. You can knock this out with a hammer and with a hammer. All right, so this is over here. This is with nitrogen. So this is what the Dross looks like with nitrogen. It's really quite similar. We ended up slowing down the feed rate a little bit to try to blow it, give it more chance to blow it out, but we really still have the same issue and the same thickness. And this is not something you can knock off with a wire wheel. When I was using a plasma torch, you just use a wire wheel and it can knock off pretty easily. You actually have to kind of grind this off with a flappy disc or a grinder. But it does come clean. You know, you can get it to be clean. And it's still accurate in terms of its dimensionality. It's just, there's a little bit more of a cleaning process. So the trade-off for us, using 125 PSI air, is it's low cost for us, and we can use the system unaltered, and we just have, there's a little bit of cleanup time to do that, to be able to use the parts.
You got a little stuff on your forearm.
Oh, nice. Well, that's the way we roll.
Exactly.
That's the way we roll. Okay, so we're going to move on to show you some examples of what we're able to get out of our laser swap with the Crossfire Pro. All right, so I first started looking at something like this. This is a 120 millimeter fan grill, and I cut this out of looks like 18 gauge, and I powder coated it, and it came out great. It's actually kind of funky. I drew this up in Fusion. I exported out a DXF and ran it through Sheet Cam, and cut it here on our Crossfire with the laser swap on it. And we probably used maybe 500 watts for this. But I want to show you some detail work on why some issues dealing with this particular platform. So we cut this this is done at 175 inches per minute. Let me see if this is going to focus on us. Okay, so what I want you to see on this is these edges have a little bit of a wavy pattern to them. They're not very straight edges. And I'll tell you why this happens. So with this particular one, and it's the same on it was the same on this one here, the powder coated one. You just can't see it very well because the powder coating kind of hides that. But this one over here is shows us that problem, that issue. And what ends up happening is this motion platform it's not very rigid. And it's not very rigid because all it's really holding is the plasma torch. In our case, we have the laser head up here. And there's a lot of motion in this whole thing. And when you're using a plasma torch, your speeds are kind of slower. There's more energy in the laser, and so we're able to ramp up the speed to like twice to 3 times the speed of using a torch. The laser cutter is just that much more efficient. But because of this XYZ platform back here, it's not very rigid, and what that ends up happening is it ends up ringing a lot in terms of its mechanical nature. And because this because this grill here has so many turns in it, in the middle of this here, every time it comes around a turn, it introduces ringing into something, either the X or the Y or the Z. It rings a little bit, and that's a result. What you end up seeing is the way that the lines that are clearly straight on this design are not. They end up having a little bit of a ripple to them. So we actually have to cut back on the wattage and slow the machine down to actually make really nice cuts. Okay. So I think this one that we showed you, click it over there. I showed you over here. This one over here was done at 175 inches per minute. This one is the same design. I turned it down to a 600 watts at 80 inches per minute. And if you look at this one, it has very straight lines in it. The impact of this is you have to slow your machine down so your machine time's longer, but you end up getting something that's very more precise. It depends on what you want. Do you want it to have a really clean look like this one? Or do you want it to have wavy look like this one? It's up for the designer on they have different options. So I'm going to show you some more examples. After I'd cut these fan grills, I went out and I got a design off of Etsy, and I did this thing here. So this is a skull I got off. No, I didn't get this off of Etsy. I got this off of freedxf.com. And this is actually made out of it's actually looks thicker than 14 gauge. This is easily at least 14 gauge. Maybe if even 12 gauge. It's very thick. And what you can see is that the cuts, they're very precise cuts down in here and in the roses. Let's see if I can get this to. Very intricate design. And because it's so thick, I was able to clean off the backside with a floppy disk and not inadvertently break any of the features off with a floppy disk.
Using a mag base.
I was using a magnetic base. Okay, so I have a magnet vise, sticks down, and then I use the floppy disk to take everything off. They cleaned up really nice. Okay, now some of these there's some things in here are not quite cleaned out. The little features still has a little bit of dross in there, but this is very interesting here. But this is what the dross looks like. If you don't clean it off, it looks like this. This is the backside of that cut. So there's a lot of dross in there on all these cuts. And because this is so precise and so thick, there is a little bit of post work to knock out all the little pieces out of this design when you're doing it. But you can get it to be pretty clean. The laser energy, like I mentioned before, the plasma, because it's moving slower, it imparts a lot more heat into the stock. And the stock heats up a lot more, which results in stock distortion as you're cutting. And so it's critical to get torch height control going on a plasma torch, particularly on thinner metal. We want to do stuff with 14, 16, 18, maybe 20, 22 gauge steel. And it's kind of critical because you're going to get distortion with that thinner metal when you're using a plasma torch. The laser has got so much more energy that's imparting into the metal that it has nearly very little heat distortion at all. And plus, the laser is moving so much faster, it doesn't impart that amount of heat. In fact, when you're cutting something and you're done, you can almost pick it up with your bare hand, right off the plasma table itself. And so, very little heat distortion. However, the thinner the metal, there's more of a likelihood that when it came out of the roller and wherever it's made, it ends up having a little bit of a bow to it. So the really thin stuff has got a lot of flexing ability in it. And so that's a challenge for us. So what we end up having is we can clamp stuff to this rack here, and or we have some weights. We have some weights like this that we use to hold the metal down onto the table, so we have it flat. So that's one of the drawbacks of not having a torch height control for this particular setup. All right, so after cutting these skulls out with this, I wanted to see just how small I could get my features to be. So I went and did this design in Fusion here, and this is 18 gauge, and it is cut at 400 watts at 40 inches per minute. Now I think this is a 2-inch square, but I'll show you in relation to a penny here. Okay, so this is kind of what we're looking at. See if this is going to go. Because this is what we're looking at here. And this looks pretty good. The backside has a little bit of dross on it, just a little bit. All right, but you really can't see it that much through the front side. Okay, so I said, well, this is pretty successful. And you notice that there's no blowouts in here. I slowed the speed down a lot, so the mechanical vibration in the Crossfire Pro kept it on path. So that's why the speed is so slow, and I cut the power down as well. So I kept going. Right, and so I did this one. This one is 20 inches per minute at 300 watts. And here's my penny. Okay. So let's see if I can hold this so it doesn't. All right, this is the kind of detail work we're going to be able to achieve with our laser swap. And this is very fine. Let's talk a little bit about future enhancements to our system here. We have had times where tip-ups are hit by the laser head, which is really unfortunate. And so we don't have any control over that because the sheet cam doesn't have a setting in it to have it avoid where it's already cut, which is unfortunate. That would be nice in a cam program to have the ability to not travel over wherever you've cut. And I'm sure some of the higher end cam programs allow you to do that, but we don't have that control. So you have to watch your thing all the time. Now we also have, our safety switch here, and then the Crossfire Pro, if you hit the space bar, it immediately stops motion, turns off the laser itself. So, but like I said, on the thinner metal, you have a little bit of bowing, and you have to clamp that down, and the clamps use up an area of your stock, so you're losing some area, which means you can't optimize all your stock material and cut everything out you want. I have been thinking about a torch height control for this, and there are a couple of approaches I thought about. One of them would be a capacitive sensor. That's how kind of the heads specifically for cutting work. And the control system in the Crossfire Pro is looking for a scaled down voltage from the plasma torch voltage, which on the plasma torch when it's running, it could be, it's some number. And they scale that down and go into the control system. It needs to be right around 3 volts, or somewhere between 2 and 3 volts. And as your material moves up towards the plasma, that voltage coming out of the plasma torch goes down, and it signals the torch height control to go ahead and move down. And so it's really about this analog voltage that comes out. So somehow I have to convert the distance from the stock with a laser into an analog voltage to trick the torch height controller into functioning correctly. So a couple of approaches I've been thinking about possibly doing is a capacitive sensor, which I could kind of design using some oscillators and some frequency counters. Another one is there are microwave distance sensors that just came out that are really relatively low priced. Waveshare has something around $20, and I could quickly acquire what the this distance is, and then generate an analog voltage to control the torch height control. And another additional thing that goes on here is the laser energy is going to go somewhere. Okay, when you're cutting, it's going to go. And it gets all the way through the metal. It's going to go down. So it's going to go somewhere. So we have an original base of our plasma table. I have some MDF that's been painted, and that laser energy is strong enough to catch that on fire. So we ended up putting down an 1/8-inch piece of plate steel down here, so that the energy from the laser goes down onto something and gets dissipated in this thing. And you can kind of see that it's getting a little bit of a potato chip to it already. And this is probably 2.5 feet down. We'd also like to put a shroud or a cover on the front side of this. We have a shop dog, and we don't want this shop dog to get anywhere near this when we're running. So we need to kind of protect this a little bit more than what we're actually doing. But you can kind of see down below here, there's a lot of debris. We've used this a lot. We love it for precision. And yeah, some additional things that we've done in addition to 3D printed parts was we took out the original slats that came with the Crossfire Pro, and we ended up cutting a series of these other slats that are pointed, and that enables us to not laser weld our stock to the slat, because the original slats were just a piece of a flat bar in there. I love this thing. This thing is awesome. You come in, turn it on, you're cutting metal almost immediately. But I'm going to turn it over to my partner. He's going to tell you, hopefully in a lot shorter verbiage than I am, because I'm just very verbal. I'm just a very wordy guy. He's going to tell you why he loves it.
Hi, y'all. I'm Rob. I'm Craig's partner here, and this thing is a game changer. I have dreamt of lasers since I was a kid, and I've used all sorts of them since 30 years ago in high school. Started with a 40-watt CO2 laser, making projects for high school and just the community around town, and kind of moved up to some Trumpf and Amada lasers through professional career, and I think those were on the 2 kilowatt range as well, maybe up to 4 kilowatts. But having this thing, I mean, Craig's really pointed out most of the benefits, but to be able to walk in, make sure the air is on, turn on the laser, and hit go, basically. It's as easy as using Lightburn with other softwares, I mean, with other lasers. Yeah, we have quite a few lasers in the shop. We have 150 watt CO2, 1400 millimeter wide laser, I believe. And we have a 30 watt fiber galvo scanning head laser for all sorts of engraving. And then this guy, and we've got robots all over the shop. We've got all the fun stuff to be able to make any of this, but to be able to throw especially a 5/16 inch thick plate on here.
Lift it up and show.
And cutting parts out of this, it's just incredible. This was, I think we're going at 12 inches a minute on this. And this is a really good example of where the air pressure makes a big difference on Dross. And also because we're using the manual head, we have to actually set the focus tube, I believe they call it, up a little bit so that you're focused down into the middle of the material once you're actually cutting. And there's a whole routine we can do to pierce that we would normally do with a professional laser cutting head. You actually have optics to focus that and do the piercing routine, but we've fine-tuned a lot of that to be able to cut all of these different gauges of material. So it's a game changer, especially to be able to do stuff like this. Even the Dross almost gives it a texture that you like. So yeah, this has changed our whole workflow and couldn't be happier.
So when I was 10 years old, I saw my grandfather on the farm do some welding with a stick welder, and I always wanted to learn how to weld, but I never got around to it until I was 57 years old. I went to Harbor Freight and I bought a flex core welder, and I fabricated a table out of some square tubing. And it was exciting because I finally did it. And that was 5 or 6 years ago. And now I have this nice shop that Rob and I are in, and we have all sorts of metal fabrication tools. And I've been striving to get to a certain point in terms of the detail work that I can envision in my head in terms of doing some metal fabrication. And it's not welding frames together and that kind of thing. And so the progression went along, and I bought this plasma table, and that enabled me to do some very precise things. And then I have a TIG torch, I have a MIG torch. I went through all these iterations, and I was watching a lot of these videos like you all have been doing, and seeing these laser cutters do their work. And up until that point, I hadn't, until we got this machine on our Crossfire Pro and did our laser swap, that I got to the level that I was really interested in when I first bought that welder 5 years ago. And this piece right here is the key to the whole thing. This was a fundamentally changing afternoon, was when we got down to doing this level of detail work, because now I can envision some designs I want to do, and I need this type of precision to do it. And for me, this is the most important piece of metal that I fabricated out of all the thousands of pieces that I've worked with. This one piece enables me to almost change my career because of this one piece of metal. So I'd like to thank SkyFire for the machine, giving us technical support along the way, offering us a position in this competition. And we look forward to hearing what the other makers have come up with. And I'd like to wish everyone good luck in winning, and go out there and fabricate something. All right, thanks for watching. piece here. All right, tell me when you're going.
Going.
All right, so I'm gonna break my back lifting this thing off the ground. All right, so this here.
So this piece is one that Craig started working on how long ago?
About 8 months ago.
Yeah, 8 months ago. And the whole concept of low poly artwork in metal is just so intriguing. There's a few people doing it, and Craig just put this guy together. And man, really, it seemed like maybe 2 weeks, but it was probably a little longer. But yeah, this is part of a piece for a shaman outdoor artwork that just changed my mind on a lot of this stuff. Can't wait to do more of this.